that are being repeated, so I'm going to skip it because we already went through it. But the intention here is I'm not going to go through the brief introduction of the finite difference time domain because we already have gone through it. I'm going to show you how we discretize a human head coming from MRI images into a finite difference time domain model. And then basically, the rest is basically the interaction of electromagnetic wave with a human head, whether we have a plane wave incident or an antenna next to the head coming from a cellular phone, or if you have smart glasses that has antenna and you are wearing this smart glasses and the antenna is transmitting and receiving. So those are the three topics. Now, the human head has tissues that are dispersive material, so we're going to use the dispersive type formulation of the finite difference time domain, which means that we can use the tissue parameters that we have characterized in terms of Debye functions, as I showed you in the previous simulation, and integrate it into the simulation based on the human head distribution, and run the simulation for one run and predict the performance at different frequencies. So basically, you have gone through this slide, and these slides we already gone through them. So I'm going to skip all this because we went through it in details. I think we can skip all this. We have gone through it. And we start from here. So this is an MRI image of one cross-section of the human head, and this is our discretized image. So we went from this one to the pixel level simulation, pixel level discretization, and this work was done more than 20 years ago when we obtained this image here. The process is basically described here. We took the MRI image in grayscale, and then basically we converted this image into a format that we can read it and process it numerically, and we ended up with a colored image. And this color image is basically discretized based on the cell size of the finite difference time domain. And we started to run the finite difference time domain simulation and produce some results. So just to show you the way we did it, the image at that time, we get it from this URL. This cross-section of the image is represented here. We converted this GIF type image into PostScript type format, which is an ASCII file that we can read it, and then we can basically process it. So this is the very beginning of the ASCII file, and you can see every 2 characters here represents 1 bit with the color of that bit. And so we read all this information and we figure out how we convert grayscale image into a color image. And at that time we were focusing on all blood and eye and brain and fat and muscle and bone and skin. And for those different tissue parameters, we were designating an area of grayscale and we're giving it a specific color. So how do we do this? From these 3 different, basically T1, T2, and BD are MRI images of the same cross-section, emphasizing certain type of tissues in that cross-section. And we use this information, we convert them into an ASCII file, we read the information and convert it to this discretized image. So to show you for different, you can see the discretized image at different cuts in the human head, how it is being converted into color images, and every color represents one tissue type. This is going up, and again, as I mentioned to you, at that time we had properties characterized all the way to 20 gigahertz. Right now we have it characterized all the way to 100 gigahertz. So if we are using a finite difference time domain cell with this dimension, and inside this cell we would see basically blocks of different material like this. When we were running this simulation many years ago, we didn't have the luxury of the memory that we can run it on, so we had to average the material here. We can't really average the material, but we use the most dominant material here, which is basically this gray area, and we assign the cell to be this gray area. So when we do this, basically this image was discretized very fine, but when we do this, we ended up with discretization like this, which still mimic the these are two different cuts, and you can see the discretization. I think this was for 5 millimeter cell size. The material properties, the material type, permittivity, conductivity, and density are described here. At that time, this was described at one frequency, I think 900 megahertz. So basically, you can see that the image of the phone that we were using at that time, we are not having phones with that image right now, but basically, if we run the simulation with a dipole antenna operating at 900 megahertz, closer to the ear, and the head is discretized like what you see it here, you can end up with a situation where the dipole antenna is propagating in free space sinusoidal wave, and when it propagates closer to the human head, you can see the wave basically goes around the head first before penetrating into the head. This image at time equal 0.6 nanosecond, and then at 2 nanoseconds in free space, 2 nanosecond and closer to the human head, you can easily see that the accumulation of the field already started to show up inside the human head. Watch for this image at 2 nanosecond and this image at 10 nanoseconds. It's basically the same kind of level of field inside the human head. I think, yeah, that gives you an image of the radiation in free space. You can see traditional sinusoidal waveform, and that gives you the image of the wave if it is coming from the dipole antenna next to the human head. So it takes some time to go completely inside the human head. It goes around the human head first before it completely goes. All the parameters of the tissues, they have very lossy material. And for example, the antenna is closer to the human head here. You can see a field stronger here, much stronger than here, because the losses it suffers going through the human head. You can see those movies and everything in those. All those are already on the website, and you can still see it on this website. Now, this is the same table I showed it to you before, how we use dispersive material. The previous simulation was running only at one frequency, 900 megahertz. At that time, we had only the properties at 900 megahertz. But when we started to look at the dispersive material much closer, and we use the Debye model, we then use Loader or Druid, although we can convert between them easily. And the method itself, we still then use the recursive convolution method or the Z-transform. This slide describes how we do the Debye model. Instead of solving for E, we are solving for D. And then after we solve for D, we know that D is equal to the complex permittivity and frequency domain times E. And then the complex permittivity is described in two terms here. And you can see the updating equation of D, or this is D as a function of frequency. This is the updating equation for D. So the first process is to update H, and then update D, and then the relationship between D and E, we bring it into time domain and apply this equation to obtain EX. So basically we have HX and EX. EX comes in two steps rather than direct step from H. Just illustration of H component, again, in terms of the coefficients that we have been using before, the same form. And the D is going to take the same form of expression with coefficients. And then once you get D, you can get E from D values. But you notice here we have to have D at n plus 1. And we need to get E at the future time in terms of the previous time and previous time. So in this formulation, you can expect that we are going to have additional three-dimensional arrays constructed for E n minus 1 and D n minus 1 for the three electric and displacement vector. So it does add a little bit of memory requirement for the technique, but once you do the dispersive analysis and run it, you can get the you can get the result for many frequencies rather than running each frequency at a time with a specific source carrying only one frequency. I showed you this slide for an example of permittivity variations and the verification with the dispersive sphere. So we looked at this now. Let's look at a situation where we have a dipole antenna. Now we are using dispersive analysis and this human model. And in this simulation, we used skin and fat and bone and blood and muscle, lens and white and gray matter. And so, no, let's see here. Okay. We use the biomaterial, and we use three terms. And for the tissues that we have used, these are the three terms coefficients. This is coming from the same work that we did up to 20 gigahertz that was published in reference 4, published in 2001. And in addition to electromagnetic interaction, we also used a bioheat equation. Coming from this reference here. And after we calculate the E and H inside the human head, we can calculate the temperature rise in the human head due to the exposure with the electromagnetic field. So this is the process itself. We run a finite difference time domain in dispersive format. We calculate the specific absorption rate, and we calculate the temperature distribution into the human head, assuming that there is no distribution of electromagnetic field inside the head. And then we recalculate the temperature distribution using the bioheat equation, using the SAR that's being calculated here. And then the difference in temperature from this step to this step is the temperature rise inside the human head due to the exposure to this radiation from the dipole antenna or other antennas. We used 8 tissues, and the discretization was 0.9 millimeter or 2 millimeter in some application. I'm going to show you which one is which. And to prove that we are using dispersive code that's operating at different frequencies, a single dipole antenna is going to resonate at lambda by 4. But when we put those two parasitic elements, we forced the dipole antenna to operate at 0.9 and 1.5 gigahertz, two of the cellular phone frequencies. This is how we calculate the SAR based on the electric field component, and the bioheat equation temperature differential equation depends on SAR. So the way we simulated this is very similar to the way we simulated differential equation for E and H. And we use this boundary condition here, an expression for the updating of the temperature inside the human head, and give you here the tissue parameters, the density, and all other C and K and B parameters that are required for the increment in time discretization for the bioheat equation. So for the power that was used at 900 megahertz is 0.6 watt, and for 1.5 gigahertz we use about 0.27 watt incident power. And the simulation results, you can see here that at two different frequencies we have 900 and we have 1.5 and 900. And we thought that we are running dispersive code, so it might be good to check the performance at two frequencies around 900 and two frequencies around 1.5. So for all those 6 frequencies, we obtain the result for all those 6 frequencies from one run in finite difference time domain. And the target here is not to look at the electric field, but to look at the maximum temperature rise. The difference in temperature inside the human head if you are exposed to radiation from this antenna that operates at these 2 frequencies next to the human head, and as a function of time. You can see that all these curves give you a rise in temperature and basically reach steady state after about 25 minutes. So if you put your cell phone next to your head, operating at this frequency, after 25 minutes, you would expect that the temperature is going to rise by about 0.25 centigrade. If you are working at 900 megahertz, if it is 1.5 gigahertz, for higher frequency, the penetration into the human head is going to be less. And also, since the SAR is going to be less, the temperature rise is going to be less, and this is about 0.15 centigrade. So these are the results that we obtained about 4 or 5 years ago. Distribution of the SAR and the temperature. If the antenna is next to the ear, you can imagine most of the field distribution and the temperature is going to be coming next to the ear. So this is for 900 megahertz, this is 1.5 gigahertz. Now, since we are using a code that predicts the performance at different frequencies, you can see basically this is a computer time run for so many frequencies, and this is if you run the code for a single frequency each time. So this is 1, 2, 3, 4, 5, 6 frequencies only. If you increase the number of frequencies, this is going to go this way, and this is going to, you can easily see that the slope is different, and using a dispersive code would be much easier and much more economically in terms of the simulation time. Instead of having a dipole antenna, now we are using a plane wave hitting a human head. And that's basically mimicking a radiation from base stations. And at that time, we were targeting multiple frequencies, 3.4, 3.9, 4.4, and 4.9. And again, we would like to repeat the simulation using one run and a dispersive code. And we managed to be able to do 3 different simulations. One simulation with this kind of excitation, we call it front above, front right, and front into the head. So we can look at 3 different simulations, and each different simulation we can predict the performance for temperature and field distribution at all these 4 or 5 different frequencies. So the level of excitation also depends on 2 types of person. One person in the tower closer to the station, and one person on the street, for example, and exposed by the radiation from the cell tower. That differentiate between public exposure or occupational exposure. And you can see at the 4 different frequencies, maximum average SAR for 3 different excitations, and maximum temperature rise for the 3 different excitations. And you can see we can reach 0.4 or 0.5, 0.67 centigrade temperature rise. You can see them here for 3 different excitations, how the temperature rise goes into the human head. This one here right in front, which is this excitation here, give you the largest temperature. The red one is the front right, which is this situation here, and then front above is basically the black curve here. And again, these are the different frequencies that are results were obtained for 3.4, 3.8, 4.4, and 4.9 in terms of SAR and in terms of temperature rise. This is one kind of exposure. Basically, you see the field here, more stronger here. This is a different kind of exposure, and this is the third kind of exposure. Now, for 5G frequencies and for smart glasses, we can have an antenna on this bridge between the 2 lenses or in the arm of the frame of the glass itself. And we run the simulation for 2.4 and 4.9 gigahertz with a human head model and also a model of the smart glasses. So we had a lens, and we have a metal frame, a plastic frame, and we have metal hinges, and we put an antenna here one time in position 1 or in position 2. Each antenna is basically composed of a dipole configuration like this that supports 2.4 and 4.9. Again, we put parasitic element to force the dipole antenna to work at 2 frequencies. We use this head with 0.9 millimeter resolution. And these are the 2 scenarios. One time we put the antenna here in the bridge area, and another time we put the antenna on the side arm. And you can see the S11 parameter. For the 2 configuration, we are operating at 2.4 and 4.9 or close to 5 gigahertz. And you can see in these figures, the radiation pattern of the antenna without the head is blue. And when you put the head, the eyeglasses and the head, you can see the deformation of the radiation pattern due to the existence of the head itself. At the bottom, you can see the SAR and temperature distribution. This is the position of the antenna. And obviously, you are going to see the distribution of the temperature and the SAR closer to the antenna in the human head. Now, if you put the antenna in front, you can expect that everything would be in front. And you can also look at the radiation pattern with the head and without the head. So in terms of maximum temperature rise, you can see in this position 2 with 2.4 gigahertz is the maximum temperature rise about 0.35 centigrade. Next to it is the same in position 1 at 2.4, and obviously at 4.9 we are going to have, these are higher frequency, the maximum temperature rise are going to be here and here. In terms of saving on time using the dispersive code, you can see the more frequencies that we are interested in, the more efficiency that we are going to get. For only 8 frequencies that we can evaluate, we reach about 60% efficiency using the dispersive code relative to traditional finite difference time domain code running at each frequency at a time. So this I mentioned already, and these are the books that I mentioned to you, the people who worked with me on this topic. And I think someone asked about dispersive material. If you search for Fatih, you will find the paper that has properties all the way to 100 gigahertz. Okay, with this, I'm finishing up, hopefully on time. And if you have any questions, yeah, I'll be happy to.
I want to see a slide.
I think
Slide 94. Slide 94.
slide number
94.
94. Okay.
SAR range such as 3.57. It's over standard for IEEE for SAR for 1G.
what you are saying is
position
3.57 is over the standard.
standard IEEE for 1 gram about
2.
300
Then it's going to be dangerous to use the antenna in position 2. This is what we got from the simulation, yeah.
I asked which as SAR is will be dangerous for head.
This is for the smart glasses.
So it will affect the head.
If you say that the standard is less than 2, then obviously it's not going to be good. But again, we're using a specific antenna. I don't know what they are going to use, the same antenna or different antenna, but at least we have the capability to present these data in terms of temperature and electromagnetic wave inside the head. So if you have a smart glasses and you know exactly what kind of antenna, what kind of frequency, how to simulate this antenna as well, then you can run the code and try to predict these numbers. Okay? Okay, you have a questions? I think the microphone is off.
لو السؤال بسيط يعني هو بالنسبه بس للتمبريتشر prediction of temperature according to the instant will on the human brain. يعني how you obtain the relation directly from the finite difference time domain.
We solve the finite difference time domain, and we get electric field components everywhere in the cross section, and from which we calculate this value, which we call it SAR, specific absorption rate. Okay, and once we calculate this from E and H, finite difference time domain, we use this equation that gives us the temperature as a function of time in terms of the SAR. So this is electromagnetic E component, and the rest of the equation is basically temperature. So we have to solve this equation using a similar finite difference time domain equations, and a form of the solution is like this. We get the temperature, these are coefficients, then we can get the temperature distribution in the human head. Okay? You're welcome. Okay. Any other questions?
You have a simple question. Have you compared with a homogeneous
Head?
Exactly. Actually, I have seen that the rest temperature is very small value. So, what would be the situation if I used homogeneous head, for example?
Not for the head, but we use homogeneous dispersive material.
Exactly.
Homogeneous dispersive material is being done and compared with an exact solution here. This is a,
From the point of view of the temperature.
we didn't do the temperature in homogeneous dispersive material, but we can do it here because this is dispersive material in the entire sphere, a homogeneous sphere. We can take the SAR from here and put it in the.
Well, I was actually expecting how much effort has been done to convert the pictures of the magnetic resonance to color pictures and convert every part to the different segment, different directions. So
That didn't take much time at all.
really,
Relative to the finite difference time domain, iteration is minimal time. Once you get it done, it's done. Yeah. So that's not a big burden on the computer. Yeah. Yeah. If we take the information from here, convert it to time, to convert it to temperature, we are going to see temperature distribution that's uniform also as well, because the SAR is going to be uniform. Okay.
Homogeneously distributed. Parameters homogeneously distributed.
Parameters.
Homogeneous material.
Yeah.